So we're going to call a curve that's been parameterized by r of t, curve C parameterized by r of t, we're going to call it closed if r of A is equal to r of B. What that means is you start somewhere and you go out and about and then you get back where you started. Okay, so you're closed if your curve ends where it begins. Okay, and then we're going to call it simple if C only crosses itself at its endpoint. So just a couple of quick examples with my laser here. This curve is not simple because it crosses itself too many times. This curve is simple but not closed. This curve is simple and closed, and that's what we're going to be looking for. All right, so probably I should draw a couple of those and label them. Let's actually slide this up, and then we can put those below here. So here is a simple and closed curve. Here is a curve that is not simple. It's not closed. So you're starting here and you're ending here. Here's a curve that is closed but not simple. Actually, I don't like the little tail that I left there. Let's, oops, my eraser is too big. Let's clean that up a little bit. There we go. Okay, so we're going to be primarily interested in simple closed curve, but I just wanted to make sure that we're clear there. All right, so one more comment on this video. This one's going to be shorter. When f is conservative, which again means that the vector field is actually the gradient of some scalar function, when f is conservative and you know the potential function for big F, so you've got your hands on little f, then we just learned that the line integral of the vector field f over c is the potential function evaluated at, I've actually written those backwards, that's bad. It's going to be evaluated at r of b minus r of a. So, all right, so what happens when c is closed? Well, when C is closed, I wish I would have erased the 0, pretend like you didn't see that. When C is closed and F is conservative, when C is closed, R of B is R of A, and so these are both the same, and so you just get a 0. And so that's something that we really want to keep in mind, is that when you're taking a line integral of a conservative vector field over a closed curve, it's automatically 0, end of story. Really, really good result to know. Now, this is true in 2 dimensions or when your vector field is a 2-dimensional vector field or a 3-dimensional vector field. But I want to point out to you a tool, a technique for telling when a specifically 2-dimensional vector field is conservative. So I don't have a technique for you yet to check whether a 3-dimensional vector field is conservative, other than for you just to go ahead and look for a potential function. I'll give you a tool later, but for now, it turns out that this vector field f, if f is given by pq, p is the first component, q is the second component, it's conservative if and only if p partial y is the same as q partial x. Now, this is one of those results where I can actually take a moment and show you why it's true, and I wanted to do that with you just because it's worth seeing these things. So you know that PQ, here we go. PQ is conservative if and only if you can write PQ as what? The gradient of something. So f partial x comma f partial y. So you know that P is f partial x. And so that means if I want to compute P partial y, I get f partial x partial y. I know that Q is f partial y. So if I want to compute Q partial x, that's the same as f partial y partial x. And wait a minute. These are the same by Clairaut's theorem, as long as f is well behaved. Now, I didn't write the caveats on f. I probably should. There are caveats on f here. P and Q have to be reasonably behaved. They have to have continuous first-order partials for this to be true. But we're not going to focus on the details too much in our class. Everything is going to work out relatively nicely. And so, in general, this check allows you to tell when a 2-dimensional vector field is conservative. And so We'll just go back here and we'll just squeeze in. These are the same by, I think I can spell Clairaut's theorem. I believe that's how you spell it. All right, so let's end this video here, and then we'll do an example in the next.